Welcome to the short discussion on the topic finding the support reactions in simple beams. This is part of this syllabus of shear force and bending moment in beams, which is one of the unit in strength of materials 1 course. Our targets for this in this discussion are uh, application of the equilibrium equations to find the support reactions in simple beams, right, when it is subjected to point loads, and in the second case when it is subjected to kind of combined loading, right. You may be having some UDL couple or any other kind of loading, right. So here two examples are taken. One is when the simple beam is subjected to only point loads, the simplest case, and then you have a combination of couples and point loads and UDL. Okay, let us look at. So this is some introduction, a little bit what you call um, knowledge on the equilibrium condition for all kind of, generally we deal with two dimensional problems only. So for all two dimensional bodies, for the bodies to be in equilibrium, we have these equilibrium conditions. As we studied in engineering mechanics, in the rigid body motion, for the body to be in equilibrium, the forces acting in x and the forces, all the forces acting must be 0, and all the moments acting on the body must be 0. But so totally you will be getting 6 number of equations, that is sigma fx equal to 0, sigma fy equal to 0, sigma fz equal to 0, similarly sigma mx my and sigma mz equal to 0. But for a two dimensional problem, we consider only three equilibrium equations, fx, fy and mz. These are sufficient and necessary conditions for finding the equilibrium of a body. So based on the equilibrium conditions only, we will find the support reactions. After all, the beam has to be in equilibrium, right? So for the beam to be equilibrium, it must follow satisfy the equilibrium condition. That means these equations must be applicable, right? So based on that background, we will try to solve the support reactions for whatever may be the loading. Doesn't matter if it is concentrated loads or a combination of the loads, you can simply follow these two steps, right? You can find out the support reactions. What are those two steps? Idealization of the loads that are given. That means what I am saying, the idealization of the loads here means whatever may be the loading given. It may be a point load, or it may be UDL, or it may be UVL, or anything given. These are the most of the times coming loads. So whatever the triangular load, whatever the loads may be given, you should first of all convert to point load. For them, in order to apply equilibrium equation, that is the first requirement. Then you mark all the support reactions. How many supports given, that many, all those support reactions. That knowledge we have, in that first chapter, first discussion we have, that how to mark the support conditions, support reactions for different kinds of supports. A hinge has two reactions, a roller has a single reaction normal to the surface. Similarly, a fixed support will have all the three reactions, that is vertical, horizontal and uh, couple, right, or moment, right. Then if you do the first step, right, then what is the first step? Idealization of the loads. So everything is concentrated load, no need to change any load, right, just put as it is. Now mark the support reaction. This is a hinge and this is a roller, right. At hinge you may have two reactions, one horizontal and one vertical, one horizontal reaction and one vertical reaction. But horizontal reaction doesn't have any meaning here. HA will be 0, although it may be there. HA is there at pin support or hinged support, but it is 0 because are there any horizontal loads are acting? Are there any inclined loads are acting? So as long as there is no horizontal load and no inclined load, don't consider even writing sigma fx equation. Straight away you can write HA equal to 0. HA in the sense reaction at the hinged support, horizontal reaction. That you can simply put it to 0. The only botheration is about the reaction, vertical reaction at the hinged support as well as roller support. So for that, equilibrium, use second step, that is apply the equilibrium equations. So you have represented this is one vertical reaction at hinge, one vertical reaction at the roller. Roller will have only one vertical reaction. Hinge may have horizontal reaction, but if you don't find any horizontal reactions or inclined loads on the beam acting, HA you simply put it to 0, right? Now you are applying equilibrium equations. Before applying equilibrium equations, you put a no, you make a decision that which direction you are going to take positive. It is up to you. You can take upwards negative and downwards positive also. Right here, for convenience, I assumed upwards positive, downwards negative. Based on that, you can look at the figure and simply mark what are the positive side and negative side. VA, VB all are the forces acting upward. So plus VA plus VB, rest of the forces all minus. Minus 10, minus 20, minus 30, minus 10. So you got it. So simply add it 10, 20, 1, 2, 3 and 1. So how much total? It becomes 70. So then you got a straight value of what you call VA plus VB. Two reactions are there, right? Upward. So VA plus, you got one equation, right? Next one is MZ equation. So here is no, you can even first apply moment equation, because you can straight away get the one value, right? Moment equation you can apply, then you can apply Fy equation, or vice versa. Either way you can do it, but to have a no proper sequence, one can apply even moment equation first, because you got a value directly, and just put that, then your another unknown also will be found out. So sigma mz at A. So one may ask, why at A? I can take in some other point, doesn't matter. You take any point where you like, right? You will be getting the solution. Generally taking its support will be beneficial. So mz at A equal to 0. If you take it, right? So when you take moment at the point A, what are the reactions that are contributing to the moment at this point? This reaction will not contribute because it has no perpendicular distance. I am standing here only A. So bring all the forces towards A, right, with their perpendicular distance. 10 has a perpendicular distance of 2, 20 has a perpendicular distance of 4, 30 has a perpendicular distance of 6, 10 has a again 10 has a perpendicular distance of 8, right? So 10 times 8, 30 times 6, 20 times 4 and 10 times 2. Add it. Okay, that's what you have to do. Here the bracket was missing, that you can put. Okay, all these are in the parenthesis. So straight away you get it. 10 times 2 is 20, 20 times 4 is 80, 20 times 6 is 180, right? And 10 times 80 is 8. 8 is 80. 80 and 180, how much? That is 260, right? 260 plus 80, 340 plus 20. 360 by 10 going to be 336. Once you got one, put in the above equation, then you will get 36, 70 minus 36 as 34. That's it. You got V and VB. That's all. These are the equations. Simply mark on the simply supported beam. One side 34, another side 36. And you can check the solution even, right? The equilibrium equations which you have applied must be satisfied, right? What is the total? Downward 30, 30. 60 plus 10, 70, and here also 36 plus 34, 70. That's it. So with the help of these two steps, you can solve reactions of the simple supports, regardless of whatever loading may be given. To illustrate this point, let's take another example with different sort of loading, with different combined loading system. So I am taking another example here. Here is a simply supported beam. There is a hinge at support A and there is a roller at the support B. And this has been subjected to three different types of loading. A UDL, partial UDL up to the point C. There is a couple, clockwise couple 5 kilonewton meter at the point, say some point at, no, let's say E or something. At this point there is some couple acting and there is a point load at the point D, and there is a what you call point B, right? These names are not given. Sometimes you may have to give your name. Always better to give a naming for the load at the beginning and end. For example, couple, you have A, you give some other, even B you can give, doesn't matter. Keep some name for the loading. So after doing that, the first step you have to apply, what is that? Idealization of the loads. right? What is this idealization means? Except point load and couples, rest of the loads, what either may be UDL given or UVL given, it should be converted into point load. That is what I mean to say idealization of the loads. Okay, and then you mark all the support reactions. So at a hinged support we discussed in the beginning, right, how to mark the reactions at the supports. So a simple support or hinged support has two reactions, one vertical and one horizontal. Similarly, a roller have only one reaction, that is normal to the surface, the vertical reaction, right? As I told you earlier, you can just make an observation, are there any horizontal loads? No. Are there any inclined loads? No. Just put this to 0. So you have effectively two reactions. One vertical reaction here, one vertical reaction here. So now you completed your first step, that is idealization of the loads and marking all the support reactions at the supports. Two reactions only finally available. Although three, because there are no horizontal and inclined loads as is no available, there is no meaning to the HA. So put it this 0, then you will have only two reactions effectively. Then you apply, right? Let's say first MZ equation you can apply, then go for this one. So if you apply MZ equation first, what happened is, what is going at where you are applying A, as I told you, either you can apply at A or you can apply at B, right? See here another beauty is that you can apply at A, right? Calculate VA VB and check your solution by taking moment at the point B. That is another way of doing checking the accuracy of your solution, right? So let's say apply at the point A, right? So at the point A, if you take moment, you are standing here, this reaction does not come into the moment, right? This has no perpendicular distance. So VA is ruled out from the MZA equation always. Even say when you take moment at the point B, then VB will not come into picture, because we are taking at the A, VB only comes, VA will not come, right? So VB you bring it to this particular point with its perpendicular distance. So VB times what is the perpendicular distance? 2 plus 4 plus 4, that's 10, right? What direction it is? Before applying itself we should have a confirmation which one direction you are going to take. The other one will be automatically negative. For example, I am taking clockwise positive, right? Somebody may say I will take clockwise negative. Yes, you can take, doesn't matter, because equal to 0 is there, your answer doesn't make any difference, magnitude will be same, right? So and you will be getting here you are assuming here anti-clockwise negative. So here VB is towards A, VB towards A, you bring the arrow this side, right? What direction it is? Anti-clockwise. So minus VB times 10. Rest of the loads are causing clockwise only. This is clockwise, this is clockwise, this is clockwise. 10 times what is its distance? 8. Okay. Then 5 directly moment. No, don't multiply with any distance. Itself a moment. It happens now. Often I used to see students doing that. So 5 directly put it, right? The direction is clockwise, so positive, and then this converted load 20 times 4 IT acting at a distance at centroid. I told you it UDL always acts at the centroid, right? So total 4, it acts at a distance 2. So distance from A is also 2 meters. So 80 times 2, okay, that is 20 times 4 times 2. So you get simplification leads to 24.5 as VB. Put this value in the first equation. That let's say what is that? Apply that equation. Sigma Fy equal to 0, which means here also when you are applying, take one direction positive, say upwards positive, downwards negative, or vice versa. You can take downwards positive, upwards negative. So when you apply that, upward reactions here VA and VB. So you would put that positive. Rest of the things 20 times 4, then this is not a direction load in the y direction, is a moment, don't consider this, and then this 10. So 24 is 80, and then 10 90, that's it. So put that back into this equation VB, then VA will be getting 65.5. Now as I told earlier, if you want to check cross check your solution, you got both VA and VB, right? You take moment about sigma mz at B. Then what you are getting? If you take moment at B, what you are going to get? You are going to get not VB, you are going to get VA, and that VA should be what you have calculated, that is 65.5. If that is coming, That means your your calculations are correct. Okay. So finally you can represent, after getting, you represent the reactions 65.5 and 24.5, and total also you can check it, 24 plus 65, right? How much is it? Is 89 and 90, right? And then this also should be 90, 10, and this is 20 times 4, 8, 80 plus 10, 90. That's it. That is how we can find. So even if we give another kind of loading is given, then also you can handle. For example, for our understanding, let's say there is a UVL acting, uniformly varying load, right? For idealization of this, what you have to do? You just take the area of this. Let us say this is 2, and this distance is same distance. Let's say 4. So what is the constant equivalent idealization of this load? Concentrated load is, it is in the form of a triangle, so half into 2 into 4, right? Half into, this is the magnitude, half times 2 times 4, this is the magnitude where it acts at its centroid. For a triangle, from the apex side you take, it will be 2/3 of this distance, or from the right angle if you take, it is 1/3. That means from this side 1/3 of 4, right? 1/3 of 4, that is 4 by 3. If you want from this side, distance from this side, 4 by 3. If you want from this side, 2/3 of 4, right? That means 8 by 3. That's all. You can, rest of the process as it is. So it doesn't matter what load is given, you can easily find out the support reactions with the help of these two simple steps: idealization of the loads and marking the support reactions, and simply apply the equilibrium equation. That's all on the topic of finding support reactions in simply supported beams, regardless of whatever may be the type of loading.